Like to start with a sentence that says that the views that I express here are my views and not necessarily seen as the pharmaceutical industry or the views of Novartis, my current employer.
Sure.
And I'd like to give you a short introduction. So genomics is about our DNA. And DNA is the carrier of genetic information, in fact, the blueprint of our functioning body. Our DNA consists of about 20,000 genes that all contain recipes to make the needed elements to develop and survive. And why is this important for us? Because DNA is a source of information. Information leads to knowledge, and knowledge leads to solutions. And what can we do with the information from the DNA? Our ambition is to have a huge impact on the lives of individual patients and their families by developing therapies for members of those families suffering from diseases. Returning to my area of work, there are more than 5,000 known rare diseases. In Ireland, circa 280,000 individuals suffer from a rare disease. This is about 5% of the Irish population. And to make it worse, not only it impacts them, but also their families. About 80% of diseases have a genetic component or cause. The genetic cause is often a defect in the DNA that is inherited from one or both parents. Now, that we can study the human genome, as we also heard in the previous discussion, in research we can identify diseases maybe caused by one genetic defect. And theoretically, we could stop disease progression by supplying that specific individual with a working gene replacing the defective one. Rare genetic diseases are often severe. 1/3 of the rare disease patients die before the age of 5 years, meaning they often affect babies and young children. They might be okay at birth, but start showing developmental problems when they get older. And the developmental problems might be concerning cognition or movement. They might stop interacting with their environment or stop being able to move or breathe. And if that is not stressful enough, most babies and their families experience a cumbersome, extensive diagnostic odyssey to find out what's wrong. And when a rare disease is finally diagnosed, often there's no effective treatment yet. With the knowledge of the genome, it's expected that more and more diseases will be found that can be treated with some kind of gene therapy. And I was asked by Ipposi to answer 4 questions. First, how is genomic data used by third parties and for what purpose? Focusing on the pharmaceutical industry, we use genomic data to make incredible transformative treatments that save lives. Treatments that are designed using that genomic data will be the treatment of the future. We only have a few today, but we're hoping that it will increase in time. There are many diseases where one missing or faulty gene is the underlying root cause for a devastating disease. Basic research institutes can utilize genomic data in the following ways: to deepen understanding of diseases, to understand how the human body works, and strangely, this can become clearer when something does not work. To support studies that link mistakes in the DNA to a way that person with that mistake develops inabilities and symptoms. To study the natural history of patients with a specific DNA defect. The previous speaker from FinGen, where they're coupling DNA with the history of patients, is fantastic in my view. And also to allow understanding of when we should and how we could modify the disease. To know if a gene therapy works, together with academia who treat patients, we need to prove that the intervention positively changes the life expectancy and quality. The aim and the purpose of using genomic data is therefore to design and create life-changing therapies for patients. The second question I was asked, are there examples of successful public-private people partnerships that involve genomic data? I think we just saw one, but okay, there are many examples of partnerships that involve genomic data. But to be honest, not all are successful. I will use the development of a treatment for a spinal muscle atrophy, a disease, as an example of a successful partnership. The defective gene for SMA, the SMN1 gene, survival motor neuron 1, gene, was this first discovered, identified in a university lab in Paris in 1995. The discovery of that gene in Paris opened the door for genetic tests to confirm the SMA diagnosis. Prior to that, the diagnosis was solely made on visible signs and symptoms of the disease: hypotonia, lack of movement, not reaching motoric milestones like controlling of the head, rolling, sitting, standing, and walking. Additionally, affected patients lost the ability to breathe, eat, and drink. Moving from Paris to Philadelphia in the US, there was a team of researchers at the University of Penn and Children's Hospital of Philadelphia who were focused on SMA. They collaborated and in a lab found a way to get the missing gene into a cell. The team of academic researchers wanted to see if this could work in animals. They got more research from patient organizations, venture capitalists, and governmental subsidies, and continued to develop the gene replacement therapy in preclinical studies. When that looked even more promising, a company was spun out of the university. That company was called Avexis. Avexis was again able to raise the money, venture capitalists, patient organizations, banks, and subsidies, to design and execute the first clinical trial to give SMA replacement therapy to patients. This first trial was designed together with academics and started in 2014 at the Children's Hospital of Philadelphia. The results of this first trial were published in 2017 in the famous journal, the New English Journal of Medicine. At this point, even more investments were needed. It takes at least 5 years and millions of dollars to design and execute the needed registration studies. Additionally, much money was needed to build the factory to produce sufficient amount of therapy, allowing treatments of all eligible patients in the world if the studies proved to be successful. At that moment, Novartis acquired Avexis, allowing faster funding of all these requirements. At all stages of the discovery and development of the therapy, patents are being made. This ensures that the money and time spent on the creation of certain steps of development, intellectual property, is rewarded. Investments are paid back. This is also the case for licensed inventions and steps in the production of the therapy in the factories. Today, one therapy has many shared partners who all share the risk, providing financial resources, knowledge, and time, and share the gains, a negotiated sum of money, a return of investment, or a percentage of sales. Developing therapies remains a risky enterprise, not always successful, and that can only be organized by partnerships, together providing scientific and financial resources, all working together. The third question was, what are the arguments for providing companies with access to genomic data? And I think we touched upon it in the previous discussion, but it's important for everyone to understand that the data that the companies receive is anonymized. Anonymized means we cannot identify the source, the person from who the material comes from. When genomic data is shared, it is with a specifically given consent. And even then, the data is anonymized. So the individual behind the data is not known. Only the person, institute, who receives the consent can trace the data back to that individual. The person can at any time withdraw consent. The data will then be deleted and destroyed. As mentioned, the data is needed to study, to find the defect, and to find ways to correct that defect. Without genomic data, there will be no gene therapy. The fourth question is, how is the pharmaceutical industry safeguarding this data? The answer is very, very carefully. We take this very seriously. Not only the pharmaceutical industry, but also the research institutes and the university with their medical ethical committees. We all take care to safeguard genomic data. The broader picture is governed by a set of laws coming from the European Commission, such as GDPR, which is the data privacy legislation. The health data information laws are now being revised by the European Commission, and these laws are called out the genomic data. Currently, a public consultation is going on. When the revised laws are issued, they will be implemented immediately and with great care by the pharmaceutical industry. For example, everyone in Novartis is trained on the data privacy principles. There's a very strong internal governance and standard operating procedures. We also have internal audits and internal inspections to check compliance with laws, regulations, and procedures. We take it very seriously. So the pharma industry is, with its strict internal processes, can guarantee that we use data only for what the patient has given consent for. The data is stored in a way that it cannot be misused and abused, and that data is deleted after an appropriate period of time. Some closing remarks. I hope my testimony makes clear that society wants the pharmaceutical industry to continue making transformative treatment. Genomic data is incredibly important. By understanding that genes are the root cause of the disease, we can design treatments to fix it by replacing, repairing the missing or faulty gene. We can bring a transformative treatment that will change their lives. With the current legislation and GDPR ruling involving the informed consent, we can safeguard the misuse of genetic data. I want to address one more way to use genomic data with something close to my heart. Genomic information can also be used for early diagnosis of rare treatable genetic diseases. In 1960, Ireland was one of the first countries in the world to establish a nationwide heel prick test for newborn. It is now possible to add PCR tests to the existing heel prick test and to find babies born with rare treatable genetic diseases. And when the babies are diagnosed, referred, and offered treatment early, this saves the HSE time and money, because the outcome of treatment of these patients is much better than patients diagnosed symptomatically, meaning often irreversible damage has already occurred. Today, unlike many other countries, the heel prick test in Ireland does not include PCR tests for treatable genetic rare diseases such as SMA. And I would like to make a plea to allow it. PCR tests are often 100% reliable, meaning no false positives, and 100% sensitive, no false negatives. For example, a PCR test in a heel prick can help to identify a patient with SMA when they're just a few days old, often before they have developed any symptoms. SMA is a relentless, progressive, irreversible disease, mainly affecting babies. If the SMA diagnosis is delayed, the outcome, even with treatments, is not optimal. In a recent survey organized by Rare Disease Ireland, found 86% of parents want to know if their newborns have a rare disease. 65% of parents are in favor of screening newborn babies for as many conditions as possible. Adding SMA to the heel prick panel for newborn in Ireland would cost 300,000 euros, and it would save the state millions. And this is just the economic view. If a baby with SMA is identified, referred, and treated early with any of the effective treatments available in Ireland, those babies will benefit enormously. By identifying and treating the patient before damages happens, the baby can develop like other babies without a disease. The heel prick program already has all data protection, GDPR protocols in place to safeguard the data. So it's not enough to have amazing new treatments, such as gene therapy, available in Ireland. The Irish patients and families also deserve to have accompanying diagnostics, such as PCR tests, as part of the heel prick. It is possible to identify patients who have a treatable genetic disease when they are newly born through the heel prick. After finding patients via the heel prick, the amazing new therapies can deliver their potential and give patients the best possible outcome. That's my testimony. I thank you very much.